Level 1, punch card. Before chips, before drives, before any of this, there was a hole in a piece of cardboard. The punch card. Each card was a grid of positions. A hole punched through meant one thing. No hole meant another. Binary logic made physical. Light shone through the card. Wherever it passed, a 1. Wherever it didn't, a 0. And it worked. Hand a stack of cards to the right machine, and it would execute your program exactly as instructed. People wrote entire software systems this way. Early banking, space missions, census data. Drop your stack and your program became a shuffling puzzle. One typo meant going back and punching a whole new card. But what punch cards gave us is still relevant. Data could be encoded in a medium and read back automatically by a machine. The materials changed. That principle never did. When magnetic storage arrived, everything changed. Level 2, HDD, the hard disk drive, a spinning metal platter inside a sealed enclosure with a tiny mechanical arm hovering just above the surface, reading and writing your data magnetically. For decades, it was the standard. Capacity per dollar is still almost impossible to beat. A few $100s buys multiple terabytes. Power it down and your data stays right where it was. But the mechanical reality creates a hard ceiling. That arm has to physically move to wherever your data lives on the platter. Every single request. A machine that takes 5 minutes to boot isn't struggling because of a weak processor. It's the metal dragging across a spinning disk. And when it fails completely. No slow decline, no warning. One day it works, the next it doesn't. Level 2, massive capacity, low cost, serious mechanical limits. The next level eliminates the mechanism entirely. Level 3, SSD. Take away the spinning platter. Remove the moving arm. What remains is a drive made entirely of chips, no moving parts. The solid-state drive. Data is written and retrieved electronically. No arm, no platter. The performance gap is not subtle. Boot times drop from several minutes to under 15 seconds. Applications open before your fingers leave the keyboard. Here's what most people never realize. When an older computer felt slow, the processor was almost never the real cause. It was the hard drive choking every single operation before the CPU even had a chance to run. An SSD swap on identical hardware produces a machine that feels completely new. People spend money on replacements when a single component change would have fixed it. But once you're running an SSD, a new bottleneck appears. Not inside the drive, but in the connection between it and everything else. Level 4, fast SSD. A standard SSD connects through a legacy interface built for mechanical drives. At a certain point, that interface becomes the new ceiling. NVMe, non-volatile memory express, solves this by connecting the drive directly to the processor through the PCIe lane. No legacy pathway, no shared bottleneck. A direct line. A standard SSD transfers data at around 550 megabytes per second. An NVMe drive reaches 5,000 to 7,000. Not a small step. A different category entirely. For everyday tasks, most won't notice or feel the difference. But for large file transfers, video editing, or compiling code, the gap is real. The drive has been taken about as far as it can go. The next layer doesn't survive a power cut at all. Level 5, RAM. Everything so far stores data permanently. RAM is the opposite. Shut the system down and it erases itself instantly without a trace. Your processor runs billions of operations per second, and even the fastest NVMe drive simply can't keep pace. RAM exists to eliminate that gap. Think of your drive as a filing cabinet across the room. RAM is the papers spread on your desk. Everything within immediate reach. Open a browser, a video editor, 15 tabs. All of it sits there. The processor grabs any piece of it in microseconds. Fill the desk completely, and the system uses the SSD as overflow. It technically keeps running, But the SSD is orders of magnitude slower than RAM. The whole machine labors under it. You feel it immediately. 8 gigabytes to get by. 16 for comfortable use. 32 if your work keeps a lot in play at once. RAM handles what the CPU is actively working on right now. The graphics card has its own, and that's increasingly the component people hit first. Level 6, VRAM. Your graphics card doesn't draw from system RAM. It has its own dedicated pool built directly onto the card. That's VRAM, video RAM. Where a CPU handles a small number of complex tasks at once, a GPU runs thousands of smaller parallel operations simultaneously. Every pixel, every frame, every texture, processed repeatedly, dozens of times per second. Memory right there on the card means no round trip to system memory. Run out of VRAM and the card borrows from system RAM instead. Frame rates collapse. Stuttering sets in immediately. What surprises most people is where VRAM hits its limit today. Gaming is just one part of it. Running a large language model locally requires fitting the entire model into VRAM. A 7 billion parameter model needs roughly 14 gigabytes. A 13 billion parameter model pushes past 26. Fill it up and the model either refuses to load entirely or slows to a crawl. Generating images locally, working with video AI fine-tuning models, VRAM is the first wall you hit. Not the processor, not a system memory, the gigabytes on your graphics card, and right now, expanding that wall costs serious money. One more layer remains, invisible to most users, running constantly inside the chip itself. Level 7, cache. Even RAM introduces measurable delay for a CPU at full speed. So engineers placed a small, extremely fast pool of memory directly inside the chip. Cache. It operates in 3 tiers. L1 is the smallest and fastest. 64 kilobytes, right beside each core, at full processor speed. L2 is larger and slightly slower. L3 is shared across all cores and reaches up to 96 megabytes on high-end chips. When the CPU finds data in cache, a cache hit, retrieved in nanoseconds. When it isn't there, a cache miss. The processor reaches out to RAM and waits. From the chip's perspective, that wait is enormous. This is why 2 processors with identical clock speeds can perform very differently in real-world use. A chip with 32 megabytes of L3 versus one with 8 megabytes determines how often the processor flows smoothly versus stalls.